webinar. On the topic, the webinar on power electronics converter for renewable energy system, organized by the Department of Electrical Engineering and Institution Innovation Council, Techno India University. We are extremely honored to welcome eminent speaker of the day, Dr. Sanjeevikumar Padmanaban, Department of Energy Technology, Aalborg University, Denmark. Sir, we are honored and thank you so much for giving your time for the students of Techno India University. I'm sure that the participants will enjoy the session and will enrich themselves on this emerging topic. As you all know, we had passed through a crisis time due to COVID-19 pandemic, but this crisis forced us to think differently. I'm really honored that each and every department of Techno India University is trying their level best to provide various opportunities, platform to the students to keep them connected academically. Now, COVID-19, there are numbers of negative aspects, but there are few positive aspects as well. Due to this COVID-19, we can reach anywhere, anyone digitally, so that we can conduct very good event for the benefit of our students. So I take the opportunity to appreciate the initiative taken by the Electrical Engineering Department to organize this webinar on advanced topic. Thank you, students, for your wholehearted participation to make this webinar a grand success. All the best. Look forward for a wonderful session. Take care and be safe. May God bless you. Thank you so much.
Thank you very much, Director Madam. Now, before I invite Dr. Sanjeevikumar Padmanaban, I would like to introduce him in front of the audience. Dr. Sanjeevikumar Padmanaban received the bachelor degree in electrical engineering from the University of Madras, Chennai, India in 2002. The master degree honors in electrical engineering from Pondicherry University, Pondicherry, India in 2006, and the PhD degree in electrical engineering from University of Bologna, Italy in 2012. He was an associate professor with VIT University from 2012 to 2013. In 2013, he joined the National Institute of Technology, India as a faculty member. In 2014, he was invited as a visiting researcher at the Department of Electrical Engineering, Qatar University, Doha, Qatar, funded by the Qatar National Research Foundation, Government of Qatar. He continued his research activities with the Dublin University of Technology, Dublin, Ireland in 2014. Further, he served as an associate professor with the Department of Electrical and Electronics Engineering, University of Johannesburg, South Africa from 2016 to 2018. Since 2018, he has been a faculty member with the Department of Energy Technology, Aalborg University, Denmark. He has authored over 300 scientific web papers. S. Padmanaban was a recipient of the Best Paper cum Most Excellence Research Paper Award. He is a fellow of the Institution of Engineers India, the Institution of Electronics and Telecommunication Engineers India, and the Institution of Engineering and Technology, UK. He is an editor, associate editor for the referred journals in participation, in particularly the IEEE System Journals, IEEE Transaction on Energy, on Industry Applications, IEEE Access, IET Power Electronics, IET Electronics Letters, and Wiley International Transaction on Electrical Energy Systems. Subject editorial board member, Energy Sources, Energies Journal, MDPI, and the subject of editor for the IET Renewable Power Generation, IET Generation, Transactions and Distribution, and the Facts Journal, Canada. Now, I request the eminent speaker, Dr. Sanjeevikumar Padmanaban, to deliver his speech. Sir, please. Hello.
Sir, you are muted. Please unmute.
Yeah. Could you able to hear me? Okay.
Yes, sir. You are audible. Fine.
Good morning to one and all. Thanks to the director, Dr. Raju Baisak, for inviting me for this interaction, for the presentation. I'm sorry, first of all, for a bit delay for my coming into the online. I first of all apologize for that. And about my presentation today, I take a few minutes about Aalborg University. I'm working in Aalborg University in Esbjerg, so the technology department. You can have a view, and this is Aalborg University, which is from Aalborg, which is the main campus of the university, which operates all other working institutions throughout the country. So about Aalborg University's education policies are based on research and education, in particularly towards humanities, social science, medicine, engineering and science, IT and design. About the students, 20,200 students, which includes exclusively part-time students, and 2,850 part-time students are available, 850 PhD students, which includes international students. About the resources, 2,230 staff members, out of which 690 are international researchers, and about administrative staff, 1,270, and overall budget of the university is around 450 million USD from 2019 20 statistics. About Denmark, so this is a view of the Denmark, a small country where Aalborg University is available in Aalborg. And apart from Aalborg, I'm working in Aalborg University in Esbjerg, which is a southern part of the Denmark. And also there is another campus in Copenhagen, which is the capital city of Denmark. And each campus has an approximately the student and the staff members statistics are given here. And about the most important fact about Aalborg University is always Aalborg University is among the top 5 university in the world for the teaching methodologies. Of course, the global leaders. Aalborg University learning goals are based on PBL, problem or project-based learning systems. For example, from the bachelor degree programs or the master degree programs, from the semester 1, the student has to gain the knowledge from the theoretical aspect, and they have to develop a project individually or in a group, most probably in a group, along with the supervisor from the university, in accordance with the societal benefits towards focused projects, especially in collaboration with industry. So 50% of the project which is given to the bachelor students or the masters or the PhD is from industrial collaboration, especially Vestas, Danfoss, Grundfos, Siemens, etc. The companies are obviously collaborated with the institution for various projects which is undergoing. Recently, about 35 case studies has been reported from the projects by the students, which is benefits the local needs of the community, of course, for the EU, and of course for the international requirements. About research, Aalborg University is one of the vast disseminating universities in the world through its publication. And now the ranking of the Aalborg University is in #1 for electrical and electronics engineering, and about overall ranking, which includes medicine and engineering and social science. So it's around 207. Among the young university, always Aalborg University is top among the 20. And young university means the university which is inception less than 50 years of old. About Aalborg University in Esbjerg campus, we have different programs, and the major programs is focused on sustainable energy engineering for bachelor, masters which has a offshore energy systems, and civil engineering we have process engineering and combustion technology. Again, oil and gas is another master programs, and risk and safety management. So these are the signature programs from Aalborg University, from Department of Energy Technology. And the most important signature programs are offshore energy systems and oil and gas. Apart from that, we have electronics program for the master programs for advanced electronics, and we also have master programs in civil, some chemical engineering and bioengineering, and we have also diploma programs for construction, and diploma programs for analog constructions, etc. So these are the programs available in Aalborg universities for which is a brand trademark signature program from Esbjerg. All the details are available in sbr.au.tk for further information. With this small introduction, let me move on to my technical presentation, what I have planned today. Could anyone confirm my audio is audible, and is there any problem with my presentation of the slides? Could you please confirm?
Yes, sir, you are audible.
Okay, thank you. Today I'd like to present some topics on electronics, which is what we have developed indigenously along with the research members of the group, and it has been already disseminated in various IEEE as well as other journals and conferences through our own ideas, which we try to figure out for the societal benefits. So about my content, the presentation will be focused on development of electronics converters, which can be applicable for electric vehicles, smart grid, microgrid, because these are the technologies we are focusing towards the prominent sustainable solution for energy needs to keep our goals in 2050 100% renewable. And about we have developed many power electronics converters which are novel solutions which are compact in size. I will be illustrating you in my preceding slides, of course with some experimental realizations and what are the application. Of course, most important is the challenges and conclusion which the future engineers going to be focused towards power electronics. Obviously, first our application requirement is for electric vehicle, because as I said, 2050 is the goal. Of course, developing countries like India, South America or Africa are focusing towards electric vehicles because to have 0% emission of CO2. So most important is the transportation, either by roads, air, or by marine. So we need to go for an absolutely pure electric based propulsion systems. Other possibility, we can have a DC microgrids, DC homes, and AC microgrids needed to be powered. So these are the application areas. And available renewable energy is mainly based on the local needs. So of course, in India we have large PV. So PV requirement is very large when compared to wind. Other possibilities, we can have fuel cells and battery. Battery is very essential because when there is a peak power available from the renewables or from the main grid, then we can able to store the energy in the battery. And of course, when the load demand is heavy or peak, then we can pump the power from the battery to the load. So in all the cases, if you look at two important common point of coupling, one is a DC microgrid coupling, which requires a voltage from 400 volt to 800 volt. So this is for the application point of view. And the source point of view, which is interconnected by the various renewable energy, we need to have between 24 volt to 48 volt. And these power transmission should be balanced. Then we need an additional power circuit, which is a power electronics converter, which has to balance between low input voltage towards high output voltage generation. So it's going to be a high power converter we need to develop. And in this case, particularly in India, we have a common grid between Kashmir to Kanyakumari. It is well designed with all standards of international regulation has been followed. But the most important is the rural areas, which includes the villages and remote areas where we can't able to bring the main grid connected towards the individual houses. So that's a big challenge because of the climatic conditions, interior locations. Of course, the most important is the budget. So in all these cases, microgrid plays a vital application because we can use the existing local energy resources. It can be a wind, it can be a sun, or it can be a tidal available within the zones. We can use the energy and we can able to power up within the community so that everybody will have electricity for their requirements. In this case, we develop a power electronics converter which is called a three-state converter. Why we call it as a three-state? Because we have three MOSFETs or three IGBTs, and these three IGBTs are triggered at three different levels or three different duty ratio, so that you can able to generate very high voltage at the output. How we frame this configuration? A simple solution. If you look at the load connected converter, the standard boost converter, a standard boost converter will convert low voltage from its input to a very high voltage at the output. So it's a standard boost converter which is available in the market for industrial applications. If you look at the input source converter, the standard inverter, if you look at the basics of electronics, so four devices will be in two legs. We replace one devices by inductor Lx. The leg 2 we replace another device by another inductor Ly. What is the purpose? When the device is closed, the instantaneous energy available in the inductor will be transferred to the load converter. So you transferring a voltage to the load side converter so that the voltage will be very high and it can develop furthermore very high voltage. This is a simple concept. Similarly applicable for the leg 2. So we are transferring all this instantaneous energy along with the source to the load side. When we merge these two configuration, then we need to look at the unidirectional power flow is very important. For keeping the power flow direction unique, we use these diodes for the adjustment so that there won't be any reverse flow of current from the load to the source. We avoid it either on the positive side, also on the negative side, to keep the current always flowing from positive side to the, from the source side to the load side. The most important aspect of this converter is very simple configuration and going to be very cheaper Of course, under the faulty condition, if one or two devices fails, it can be easily replaced, or entire circuit can be refabricated at lower price. So now we designed the converter with the basics of electronics with a new idea. Then we try to figure out the theoretical background. What is the benefit? We are trying to use the converter from 10% to 60%. That's most important. We are going to use the renewable, which is connected on the input, from 10% to 60%, the maximum utilization. So when you are going for a 60% utilization, the power is 100%, but you are using only 60%, we are getting a gain around 42 times when compared to the existing solutions. So these are the existing solution we are shown here, and the proposed solution is going to provide you a gain of 42 4 times. That's pretty higher than the existing solution. So we designed the converter, we done some theoretical background to emphasize its characteristics. Then the most important is in real time is going to be the losses. So it has active components, MOSFETs, and passive components, capacitors and inductors. So we need to know what are the losses. So all the three devices which is available in the configuration provides internal resistance with the losses between 16% to 17%. The diode has its own internal resistance. The diode provides a losses between 4.8% to 5.2% maximum, each diodes. And about the capacitor, which produces the losses between 6% almost, and the internal resistance of the two inductor Lx and Ly can create a loss around 9%. So we know the complete information, the statistics, how much loss is going to be created before putting into the application. How do we find this information? All based on the data sheets we choose on the component from the existing solutions and the manufacturer's parameters from the data sheet. Then we calculate it in real time, of course, in simulation model. Then the experimental results comes into the picture. As expected, we want a 400 volt at the common point of coupling for various applications. So we generated almost 400 volt as per the requirement, the maximum utilization factor of 60%. And this is very important. These are the input current through the inductors. If you look at the shape of the current is very smooth and periodic. That's most important. There won't be any short spike or unwanted behavior. So that these currents play a critical role in creating the reliability and durability, or of course the lifetime of the renewable which is connected on the input side of the converter. Suppose this current is going to be highly discontinuous or non-periodic, then you lose the characteristics of your PV. For example, the PV is designed for 25 years. When you are not properly regulating your converter, so that the PV lifetime can come up to 1 to 5 years. That's very important when a power electronics converter is connected to a PV or a fuel cell or battery application particularly. And these are the voltages across the device, the MOSFETs, which is around 185 volts, which is shown between drain to source. So it boosted to 185 volt, whereas the input is only 48 volt. And about the voltage across the diode, which is also around 185 volt, which is a further confirmation that the converter is working to the expectation. And here the diodes are working on forward bias condition as expected, which has been applied for the purpose. And the most important next investigation is about the regulation, because all the loads are not constant. One utility application can be 100% power required, another can be 50%, another can be 25%, another can be 0, of course, because it is maybe in off condition. So all these conditions, the power electronics converter has to regulate the power uniquely without having any huge distortion. So that's why we try to figure out the power from a maximum value of 395.2 volt. I said 400 volt is generated here. It's look like that, but in real time we can't get 400 because there are switching losses, conduction losses, passive losses, of course electromagnetic interference, etc. Because of this we can't get exactly 400. After compensating all the losses, we are getting around 395.2 volt, which is pretty good, and we are regulating towards 206 volt minimum. It's our own design to understand how the system is working. So all the cases, the voltage propagated in a very smooth fashion without any huge peak overshoot, settling time, or any unwanted behaviors. So the system is well governed and propagated. Whereas the input voltage is always kept at 48 volt as standards. So 30 volt as standard. So we kept 30 volt as an input from the renewables. So 30 volt is the standard. So it is not regulated. So all the cases, the voltage output is regulated. And of course, this is the input current, as I said, very important. The current to the inductor, they smoothly vary from a maximum value to the minimum value as the voltage is regulated. And this current, as I said, should be very smooth. Otherwise, you will cause damages to all the renewables which is connected on the input side, either a battery or solar or fuel cells, most important. And of course, the load current is regulated according to the load requirement from the maximum value to the minimum value. And we have shown here a very clear picture how the input current regulation has been done from 16.59 amperes towards 4.67 ampere. You can have a smooth shapes and only the amplitude is changing. That's very important, as I said. How we are getting all this operation? Pretty easy, because we have 3 devices. We are controlling 2 devices and the third device is fixed at 35%. So that first device is conducting for 50%, second device is conducting for 35%. We are getting 395.2 volt. When you are keeping the conduction period as 35% for the 2 devices, then we are getting 206 volt. So by controlling the 3 devices, we are easily regulating the power requirement for the load demands. And about an experimental prototype, you can have a look. This is the compact size of the converter. As I said, if a MOSFET or a passive component, a capacitor or inductor fails, we can easily replace, or we can easily replace the complete block set, because the converter is cheaper components and a cheaper price. We can completely replace by a new one. And this is a complete view of experimental prototype. So we are capturing all the results using advanced oscilloscope, and PWMs which is going to trigger the converter is generated from an FPGA based solution, which is also a compact digital processor with a high speed solution sampling rates. And this is the shape of the converter, which is very compact in size, and all the loads are regulated using standard resistance. And again, I showed you 2 regulation points, is very important. One is for 250 watts and 350 watts low power. As always, the input voltage is kept at 30 volts, whereas the load generated to 400 volts. The first case, we have minimum power 250 watts. Accordingly, the current is generated with an average value of 4.71 ampere. You can have a look. And the most important, this is ripple content. And the ripple content are satisfied according to the IEEE standards of less than 5%, the peak, up peak and the lower peaks. Of course, for the 350 volt, as the load is increased, obviously the current has to increase, so it goes to 6.86 amperes, whereas the input voltage is kept 30 volt and the load is also 400 volt as expected. And the load current is around 0.93 amperes, whereas in case of 250 watt, it's 0.26 amperes. You can have a clarification that as the load increases, the load current also increases. Single stage quasi is a sort of inverter. If you look at the
Hello.
CY is going to be 2 volt. So all these voltage fluctuation or typically I can say it's a ripple factor or within the limits of IEEE standards, so that we are having less than 5% distortions, even 1%. And the most important one is, once the converter is designed, we are looking for the theoretical aspects, how the converter is beneficial comparing to other solutions. So if you look at the utilization, I want to utilize this DC power from the renewable between 10% to 30%. Then around 30%, I'm getting 22 times the gain, which is much pretty better than the existing solution, which is not possible. So this configuration with a slight adjustment of passive components, we are getting 22 times when the utilization is only 30%. The most important is the loss analysis. Ideal condition, we can go for the maximum gain around 200. But when the losses are considered, because there is an active component like MOSFET IGBT, then you'll have switching loss, conduction losses, passive losses, of course, the EMI losses, etc. Then the power comes around 194 something. So it's obviously acceptable at 30%. We also invented further complex X converters, which is also called as a modified CP converters. In modified CP converters, if you look at the load side converter, is a standard boost converter. On the input side, we included additional inductor between the capacitor C1 and S, which is Ly and LZ. So these three inductors plays a critical role to enhance a very high voltage to the load requirements. When the device is closed, the stored energy or instantaneous energy available from Lx will be delivered to C1, Ly will be delivered to C2, and Lz. All these combination will be delivered to C3. So you will get a very high voltage, the output compared to the existing solution. So the converter is designed. Most important plays a efficiency. We are trying to figure out between 60 to 100 power efficiency, maximum power efficiency. We are trying around 100 watts. It's going to be 91.4%. You can ask me why you are having so less efficiency, not near to 100%. I say 98% or 99%, because we are using the components of very high voltage and high current, but we are trying to figure out the results in the laboratory scale with low voltage, because the laboratory, for the security purpose, because it's a DC, we are regulating all these converters and testing the performance at low voltage, because 24 volt we are getting 120 or 300 volts, depends on the configuration models. The minimum is 400, the goal is 400. So keeping a voltage of 48 volt, we are getting 400 volt. It's very high. And if you are going for a very high voltage, like in 1000 volt, 2000 volt, or in kilowatt or megawatt, then it's become very tedious process handling in the laboratory scales to create a protection. That's why we are testing all this converter at low voltage profile. Once a converter is designed, we know about the efficiency, the requirement which can obtain from the real time. Then the most important is the loss analysis. The device which used in this converter is around producing some 47% losses, diode between 13% to 12%, inductor is around X inductor is around 10%, and the inductor Ly is around greater than 1%. The capacitor is around 5%. The combination of Lz, C2 and C3 is around 0.4%. So the complete distribution of the losses is known. It's very easy to test the converter in the real time. Now the real time testing, we try to keep the input as 24 volt, and the output voltage is generated around 172 volts, only a factor of 30% utilization of the DC bus. Whereas the load current is around 0.51 ampere as expected, and this is very important. The current through the inductor, the input current through the inductor, they are very smooth, periodic in nature. There is no any short spikes or deviation, so that all the inputs which is connected on the input side of the converter are safe enough. And these tests are conducted in continuous conduction mode, or I can say a simple word for a non-electrical background people is a linear mode of operation. And we are trying to understand the converter for a very high non-linear operation. For example, inductor is not a linear property of the converter system, a passive component. So there is a high linearity available in the converter. So we are trying to figure out by increasing the frequency of the device above the expected rate, then we find the converter, put into the converter in non-linear mode, and we find the diodes voltage are shifting between 92 volt and 152 volt. Usually it has to have only one peak, but here we are having a two peaks. It means the converter is working with a very high linear operation. Further, the current through the inductors goes to the peak and comes to the zero. It also ensures that we are making the converter to work in a very high non-linear mode. Even in the high non-linear mode, we are able to propagate the converter with a maximum voltage of 92 volt. That's pretty good. So this all ensure the converter fits to a linear as well as a very non-linear mode, which is technically called as discontinuous conduction mode. Why it is required? Suppose the load is going to be a DC motor, the possibility of making the converter into a non-linear mode or DCM is very high opportunity. High opportunity when the converter is connected to a highly non-linear load like a DC motor. Then we need to make the converter to operate under this condition so that the motor can be propagated continuously, even there is a high discontinuous mode of current appears. Further, we also develop converters based on a multi-stage. If you look at the configuration, this is a standard half-bridge inverter. You can find in the textbooks of electronics, which is applied in the real time, the industries. Two devices, connected across the loads in one lane. Then we've connected an additional combination, which is the capacitors and diodes in stacks, cell 1, cell 2, or in stages. As the stages increases, you can able to get a very high voltage at the output. Further, this voltage can be outputs can be connected to a inverter. We can able to connect to a motor or to a AC grid. On the intermediate stage, we can able to connect to the battery, so the power can be stored. When there is a peak demand on the load side, we can pump the power from the battery to the load. So these are the flexibility of this converter. Once we design the converter, the most important is the number of component requirement. When the number of component requirement is 0, diodes and capacitors, then it becomes a standard half bridge inverter. Now, as the stages increases between 1 to 6, if in the stage number 6, then we are going to use 12 diodes and 12 capacitors. So you can have an idea how many component is required if you're going for stage 6. Once a converter is designed, then we look for the requirement of passive component. Then the most important is the utilization. So if you're going to utilize the input power from 10% to 90%, obviously when the 90%, you can get the maximum operation of the region, the maximum gain. Suppose you are going to use 10%, this is your operating range. Is between, I say, 20%. So when you're going near to the 90%, you get the maximum power out of the converter. What is the future of this? All these compact X converter what we develop? They are obviously free of magnetic losses, because we are not using high frequency transformers or coupled inductor. Usually it will be available here, the stage between the input converter and the load side. They use isolation transformers, high frequency isolation transformers, or coupling inductors. So these may create magnetic losses, and of course they can create a huge ringing effect on the devices, so that you need to go for a very advanced modulation methods, which includes 0-volt switching and zero current switching. And making these algorithms can make a little burden to the device, to the processors. So we need to have a compact coding and can create a little bit burden with the sampling with the processor. But in the cases what we analyzed, we use a simple PWM, a simple hot switching, trying to get the maximum power from the converter. So it's very easy. Even under the faulty condition, the stages can be easily replaced, because it's just a combination of diodes and capacitors and cheaper price. And as I said, we always use 1 or 2 or 3 maximum devices. So we don't want a most advanced, sophisticated digital processor. By using a simple digital processor, we can be able to effectively control and get a very high power from the existing renewables. And most important in real time is microgrids. As I said, all these converter fits into the requirements. The most possible locally available are either PV, wind, and of course we need the battery. How we can connect the common point of coupling, the load application of electric vehicles or any AC motors or grid. Then we need to connect a PV through a DC-DC converter. For a wind, obviously all the windmill has a turbine with AC machines, because either it can be induction generator or it can be a common point of coupling. And then we are having a battery, because battery is going to be bidirectional. We need to store the energy in the battery. Of course, the stored energy has to be delivered to the common point of coupling. Then we need a bidirectional DC-DC converter. So it's a standard structure, conventional model. And we are trying to figure out with our own electronics converter, where we can have a multi-port converter. A multi-port converter can have a multiple inputs. So PV can be connected as to the one input. Wind can be connected through a to connect the battery. These power can be fed out as a single output to the common point of coupling. And we can use the same application as like a conventional model. In this case, we propose a 3-port converter, port 1, port 2, and port 3. Because 2 are input port and third one is the output port. That's why we call it as a 3-port. So 2 ports are dedicated for the input side and 1 port is dedicated for the load side. The input ports includes a PV power. Another one is the battery. If you look at the closed configuration, this is a standard boost converter and this is a standard buck converter. A buck converter will generate high voltage to low voltage and a boost converter will convert a low voltage to high voltage. Then we merged these two converter by through additional devices, DC and this one and MOSFET. So the power flow will be merged as a combination of these two and delivered to the load side as a summation. Why we need these converters? Very important, because to keep the maximum power point tracking. So daytime we will have a maximum PV power from the sun. If there is a wind, then we will have a maximum power from the windmill. Of course, the battery will be stored, depends on our load requirement. So all the cases, there is a discontinuity between the power flow between the three connected inputs. So we need a stability on the load side to have a maximum power. So these power electronics converter will regulate all these MOSFETs and IGBT, so that try to keep the power always at the maximum. Suppose the power goes on your anti-clockwise direction, by adjusting the MOSFETs and IGBTs, we bring the power to the maximum level. Similarly, if it goes towards on your right side, of course, we can bring back to the maximum point of tracking. So we need a sophisticated converter able to give you the maximum power under different radiational conditions. And these are some of the experimental results for a 60% utilization and 40% utilization of the sources. First case, we keep the PV like a battery, 12.5 volt, and the current generated from the battery is around 7.9 ampere. You can have a look on the current. That's most important because it's very periodic, and there is no any sudden change in high current. That's well protected on the PV side. And this is the output voltage, which is around 24 volt. We double the output from PV, and the load current is required is only 3.6 ampere. And these are the signals of the voltage PWM available for the MOSFETs, and these are the currents available on the inductor. As I said, it's very important because it governs the durability and reliability of all the renewable which is connected on the input side of the converter. And keep note, these all testing is done for 60% utilization of the input power. Then we try to figure out 40%. In this case, we keep the PV power maximum 30 volt, and the current generated from the PV is around 800 milliamps, and the load is stepped down to 18 volts. So we just shown a vice versa condition of the previous one, and the load current is around 980 milliamps as per the requirement of the load for 40% utilization. And simultaneously, we have shown here the voltage for the PWM for the MOSFET, very smooth. Now, of course, these are the current to be governed because these current play a critical role in keeping a long time utilization of all the renewables. So both the cases, the ripple factor is less than 5% as per IEEE standards. Most important, how we are performing all these tests. Before putting into the application, we try to figure out in a numerical simulation model. In numerical simulation model, we are trying to figure out between 20% to 80% utilization. The efficiency obviously goes near to 98%. In real time, as I said, there are various losses, passive and active losses, and switching and conduction losses. We are getting the maximum efficiency is 93.6%. How the algorithm are developed? The proposed converter, 3-port converter is available here. We are trying to sense the parameter of the PV current, PV voltage, battery current, battery voltage, output voltage, and output current. And we create an algorithm in the FPGA with a multi-objective controller. The purpose is to decide the power flow direction, battery management system, mode of operation, and duty cycle, which is required for all the MOSFET or IGBT available in the converter. What is the algorithm? Start the program. We are trying to check what is the power of the PV. If it is greater than 0, go to the next step. Check the power of PV is greater than the maximum output power. Yes. Then go to the next step. Check the current of the battery. If it is greater than the maximum battery current, then connect PV to the load. No issue. If fails in the first step, PV power is not greater than 0, then connect the battery to the load because PV is not sufficient to deliver the power to the load. So battery will deliver. Second step, if PV power is less than the maximum power PV plus battery, because PV is not power of the battery and we connect to the load. If you are failing in the third step, if the battery current is not greater than the maximum battery current, check for state of the charge of the battery. If the state of the charge of the battery is 90%, yes, no problem. We can connect PV to battery, then to the load because it powers the battery and both the power will be pumped to the load. If it is less than the 90%, then we have so battery is not sufficient enough to keep the power to the load. So the most important is state of the charge for the battery. So that's why we need to have appropriate monitoring systems to the battery to keep the power for the requirement of the load. Further, recently we invented this electronics converter. We call it as a triple mode active passive parallel intermediate linked converter. If you look at the load side, is a standard boost converter. On the input side is a standard half bridge inverter. So on the first leg, we replace the MOSFET by inductor. On the second leg, we introduce a new change. We put an inductor, also a capacitor. What is the purpose? When the device S1 is triggered on, the instantaneous energy available in the inductor will be stored. And when the device is open, all the instantaneous energy will be delivered to the capacitor. So stored energy will be delivered to the load side boost converter so that we can able to generate a very high voltage at the output. So in order to the requirement of your load, you want a very high voltage, we can able to increase the leg from 1 to n. As a stack we can increase so that we can able to get a very high voltage on the input of your boost converter and you can deliver to the load. Once the converter is designed, we are looking for the power in watts. We are trying to figure out a very low power in the laboratory scale from 100 watts to 500 watts. Obviously, when there is a 500 watts, the efficiency is far better. In numerical model, we are getting around 97% efficiency, but in real time, it is going to be 93% efficiency because of various loss compensation. How these converter can be fit into your application? So this is a common point of coupling, DC microgrid. On the right hand side, we have the application part. On the left hand side, we have the utility power supplies. One from the windmill, it can be connected through AC to DC conversion. From DC to AC conversion, then we can use AC to DC to couple to the DC microgrids. Other part is the existing AC transmission lines, which can be connected through a AC voltage regulator, two anti-parallel connected thyristors. Then we can connect to a AC to DC, we can couple to the DC microgrids. Other possibilities, we can have a battery bank, which is connected to a DC to AC converter, then fed to AC to DC. So when the power available in the generation unit are very high, we can store in batteries. And during the peak demand, we can pump the power from the battery to the DC microgrids. On the application side, we can go for electric vehicle charging stations, which is connected through DC-DC converters. Of course, we can be able to charge the vehicles. The recent technologies are focused towards vehicle to grid so that the consumer become an entrepreneur. We can gain the margin of financial benefits from the grid operator because you are going to pump the power from electric vehicle to the grid. Other possibilities, we can pump the power from PV to the DC microgrid to DC-DC converters, and other applications like laptops, iPods, mobiles, camera, etc. We are using an actuator called DC-DC converters. In real-time application plays a critical role. As I said, we are keeping our input renewables only at 40 volt as a standard model, what we develop. And the output voltage is generated around 400 volt. And this is the output current, which is around 1.4 amperes. And this is the current through the inductor, very smooth and periodic. That's most important on the input side, well protected for all the renewable which is connected. And these are numerical testing with simulation software. In real time, obviously, the factor will changes. As expected, we are keeping the input voltage 40 volt exactly, but the load voltage reduced to 394.4 volt because of various losses. We can't get exactly 400 in real time. And these are the currents on the input side. As like the numerical modeling, we are getting the same behavior. And this is the load current. The load current is little less than the numerical model because obviously the output voltage also reduced to 394.6 volts. And these are the parameters very important. We are using multiple capacitors. All the capacitors store the energy according to the load capacitor. They generate the voltage and they keep limits of ripple less than 5%, which I can verify. I will show you. And this, which is very important, periodic. For the capacitor voltage, very smooth. There is no any hazardous behaviors or short spikes, so that they behave very smooth and ensure the reliability of the capacitor operation with less than 5% ripple content. And this is the output voltage. As I said, they are generating near to 394.6 volt, not 400. And this is the input current, very important. And obviously, all the results have been verified in accordance with the theoretical hypothesis what we developed. And in electric vehicle, how these converter play a critical, that's most important. If you look at electric vehicles, we have different electric vehicles, fuel cell based electric vehicles, where the fuel cell is the prime mover. So here we will store the hydrogen through fuel reformer. Will convert, and with the fuel cell we convert these hydrogen energy into DC, and this DC and power is very low power voltage. So we need a DC-DC converter to convert the low power to high power. Then we use an inverter which converts the DC to AC. Then we regulate all these AC motors. It can be an induction motor or permanent magnet synchronous machine, or depends upon the luxurious need of the electric vehicle. And other applications, we have luxurious needs, lighting, air conditioning, etc. Also pumped from the fuel cell power generation unit through a DC-DC converters. If you look at closely the efficiency, the 80% efficiency is governed by the power electronics converter when compared to the fuel cell is around 60% power generation from fuel cell. And this model is a typical model of fuel cell based electric vehicle. We have hybrid model also, fuel cell based hybrid electric vehicle. Along with the same model of fuel cell, we will put a battery along with the capacitors, ultra capacitors. So in this case, we can able to store the energy from the DC-DC converters as a backup. Of course, during the peak demand, we can pump the power from the battery to the driving unit. So recent technology, you are applying the brakes. Region available from the motor can be delivered to the battery, and you can store the energy. Even in these cases, the 80% of the efficiency is controlled by the electronics converter when compared to the fuel cell generation is around 60% efficiency. Then we are going towards transportation application, heavy transportation, that is most important. It can be a electric large scale or small scale. For example, low duty vehicles, the same application plays a critical role with fuel cell power generation. We need to incorporate all these electronics converters, battery unit to control the requirement of the regulation of your motors. Whereas in case of heavy duty vehicles, we need to have an individual microgrid within the electric vehicle. It can be a ship, it can be a road transportation, of course it can be air transportation. Then we need a DC microgrid within the electric vehicle. For example, here I showed you a electric vehicle which is on a roadside, large scale truck. In this case, the battery requirement is between 600 to 700 volts, which is controlled by battery controller from the point of view of common point of coupling. Then obviously fuel cell will be the prime mover, which is connected to a DC-DC converter, and the power is coupled to the DC microgrid. Then from the DC microgrid, we can use the DC power to convert to AC to drive your motor for the propulsions. Of course, this DC energy can be further converted again back to AC to use 20 kilowatt additional loads available in your electric vehicles, which is used. And we also have luxurious requirements, lighting, air conditioner, protections, etc., airbag, etc., which is around 25 kilowatts. This can be pumped from a electronics converter, DC-DC converter, from the source of fuel cell. Then we can pump the power. So this is a complete power requirement for a standard heavy duty electric vehicles for road transportation. So we developed many converters. As a summary, I can show you here. Our classical comparison is always with the number 3. Transformer and coupled based inductor based converter configurations. Usually they are the standards they are adapting. We always compare with this configuration. So if you look at the reliability of the standard models is average. The cost is very high because they use magnetic components, transformers, high frequency transformers, etc. And efficiency obviously very high because they use a transformer. It can deliver the low power to a very high power to the load side. And advantage, we can have high power applications. Soft switching is possible by turning the ratio of the transformer. You can regulate the power. But disadvantage, bulky. Of course, there will be a lot of magnetic losses. Then we have to go for soft switching technology, as I already illustrated in my previous slides. The application can be for heavy duty vehicles with a high power. But 1, 2, 4, and 5 are our own converters we develop for electric vehicles and microgrid application, and we find that XY family always very good with a high reliability, average cost when compared to the standard model. Obviously, it has a very high efficiency. Advantage, we always use 1 or 2 devices, and the structure is extendable very easily with low cost. And disadvantage we have because we use a lot of diodes and we can create a lot of discontinuous current. As I explained you, we showed a results between continuous mode and discontinuous mode. And this converter can be applicable for either high duty or low duty vehicles. Of course, we invented other configuration like switched capacitor based converters. It can also be applicable for low duty and low power application, not for heavy duty. And of course, we have also investigated switched inductor-based converter, which also applicable for low duty and low power application. And multi-level converters, this is applicable only for high duty. So with our own developments, 1, 3, 4, 5, we find X5 applicable for both the cases, low and high. Finally, I like to give you some inputs how the challenges of the power electronics play a critical role in microgrids and electric vehicles and renewable energy application. First is need to improve the efficiency. In order to improve the efficiency, all the renewables, of course, electric vehicle, most of the mechanical and hydraulic parts needed to be replaced by electric motors and power electronics components. Then they become a compact size, easy controllable, and under faulty condition can be easily replaced. For choosing all this, most important is the selection of power electronics component. How you select the power electronics component? Before selection, as I said, we should know the complete information of LAS analysis. That's most important, and how we are going to adapt the control strategies and EMI filters to compensate electromagnetic interferences. Of course, selecting a proper combination, how we are making a hybrid model. It's a hybrid model between a PV and solar, PV and wind, or PV or fuel cell, or fuel cell, PV, wind and battery going to work. That's most important. And how to increase the durability of the renewable. That's also very important. Durability means, example, if you are using battery, the charging of the battery, of course, the discharging of the battery is controlled by a DC-DC converter. If the ripple content of the DC-DC converter is very high, then you're going to definitely kill the battery in a short period of time. So it's very important how you are going to control the ripple content on the input current, of course, on the load current, and the state of the charge. So this all maintained decided by the power electronics converter. Depends on the component selection and the related power electronics converter. For a power electronics converter, it is going to be put it into the application. Maybe a wind application will have a lot of vibration. Since there is a low flow of a high current, then there will be a thermal losses so that the tracks or the components can be spoiled off. So we need to have a proper vibrational arresters, proper cooling system. Nowadays we are having very advanced fan cooling, oil cooling, and of course we are having shieldings. Apart from that, heat sinks, we have so many options are available for protecting the power electronics converter from thermal effects. And of course, the challenges for the engineers lies always within to create a high efficiency. The system should be rigidness, and the cost always should be very minimum and should be compact size, very small. How to increase the performance of the renewables and EV? How we can increase the performances? It always depends on the selection of digital signal processor, because the processor decides the signals to control the electronics converter based on various inputs from input side as well as from the output side. For example, I show you a control algorithm where we sense the battery voltage, battery current, PV voltage, PV current. So sensor should be very accurate, should send the information towards the DSP fast sampling rate, and the algorithm should be very fast so that desired within less burden effect of the processor. The most important is the safety in your renewables and EV. Again, for the safety, the sensors plays a critical role. For example, in case of a motor, you have to keep a sensors on the stator, rotor, and bearing to sense all the thermal effects, flow of the brakes, etc. Even there can be arises a fault in your bearings by a crack. This needed to be sensed. So now we have advanced IoT sensors that plays a critical role in acquisition of these parameters and provide the information to the DSP, and the DSP very effectively in a short period of sampling, because it's already been programmed for the expectations. Of course, in modern electric vehicles, the ABS system, which is a protection, airbags now, or using power electronics converter called as actuators. The DC-DC converter in electric vehicle, they call it as an actuator. So these actuators can trigger the ABS systems and airbags during hazardous condition of the electric vehicles when an accident is happened. So we can protect from a huge catastrophe. In the previous case, these actuators are used by hydraulic system. They are very big and complex system, of course, very expensive. Now it has been replaced by a very compact, tiny power electronics converter. All these actions are obviously carried out by power electronics converter in coordinate fast sampling digital signal processor. So the safety is controlled typically by power electronics converter by the action. Of course, the action has to be taken by the DSP. At the end, the most important is for all the electronics engineer is the cost. We need more luxurious things in the electric vehicles or for our home needs through microgrid applications, but we need everything. Selection of the renewables, selection of our luxurious needs decided by electronics converter and its component configurations. So the challenges always lies for designing high reliability, high quality performance at low cost. Finally, I like to conclude that we have developed many electronics converter for renewable energy application. It includes the electric vehicles using fuel cell powertrain, and of course for microgrid applications. Develop electronics converter can be applicable to any HVDC systems so that will feed for the application with low power inputs. Obviously, all these converters are designed with cost of optimization, high efficiency, minimum number of components. So the structure is modular and easy controllable with available DSPs and any digital processes. So we have developed many converters. Among them, multiport converters and hybrid converters are very effective because they can have multiple inputs and single outputs, well controlling the maximum power point tracking of the renewables, which is connected on the input side. And of course, we are focused towards lower cost and eco-friendly, and there won't be any emission from electronics converters when applying with fuel cells. Thank you one and all for your attention. If you have any specific questions, I'm happy to respond.
Oh, thank you, sir. Thank you very much. It is really wonderful and full of technical information. Thank you for illuminating this technical webinar. Now the house is open for the questionnaire. So if anybody have any question, the speaker is ready to answer. Anybody from the audience, any question? Hello.
See, I've got a question. I've got a question.
Sir.
Yeah.
Mr. A.K. Pal have some question and he will moderate the session also.
Yeah.
Sir,
Yes.
For the electric vehicle, mean the electric bus. See, are you using what sort of power device you are using for a say 60 to 75 kilowatt for a 60 to 75 kilowatt DC motor? What sort of device you suggest?
Device means in what aspect you are asking? Could you please
Yeah,
clarify?
IGBT,
Electronics or you are asking?
electron device, mean IGBT or any other advanced thing.
For example, in companies, because they go for, obviously in present technology, they use MOSFETs because MOSFET are cheaper solution, readily replaceable, and it can be operated for a high frequency. When you are operating the converter at a high frequency, the component requirement of the capacitors and inductor comes down. As you increase the switching frequency, the size of the converter component requirement comes down. So it's a basic principle. When you're going to increase the frequency, you're going to reduce the size of the capacitor and inductor. For advanced sophisticated systems, for having more sensitive performance, we are moving towards advanced component. For of course, we are going towards a GaN because these are on research. Application, the existing electric vehicles, obviously all the companies will go for MOSFETs because the most cheapest solution, or if the next level is IGBT.
Okay. Got the idea. Mean the MOSFETs are preferred because of high frequency application.
Yeah, because high frequency application, you don't want large capacitors and inductors.
Okay, we have a question from a participant. Okay.
Mr. Himanshu, you can ask the question.
Yes, I'll give talking option to him. Just hold on.
I can see a lot of questions here.
Yes, Himanshu, you can talk now.
Yes, good afternoon, sir. Thank you for your interactive session.
Okay.
Actually, I have seen in capacitor, actually, most of the explosive element. In IGBT, some cases we see the failures due to capacitor. So what are the safety precautions taken in most modern converter?
A simple example I can give you. because we developed this multiport converter and this converter, which are having more capacitors than similar to AC converter. We have many capacitors. You can have a look. We try to keep the limitation of the voltage, I mean the ripple factor, within the limitation. It all decides how you are going to trigger your converter. For example, if you are triggering your converter non-periodic manner, if there is any problem with your digital signal processing unit which creates huge spikes, then the possibility of getting spoiling the capacitor is very high. We can't do nothing with the capacitor because modern polarized or non-polarized capacitors, obviously how we are going to trigger these MOSFETs plays a critical role. So all the cases, we try to keep the PWM very effectively by designing a modern driver units with surface mounted components. You can see this is a very advanced driver units. If there is any fluctuation, for example, if there is any short spikes comes out of the digital signal processor from FPGA or any DSP, these driver units are well governed and well designed so that these short spikes can be nullified, and we are always giving to the converter very smooth PWMs, I mean square waves. So in this case, all the capacitors are well protected and safe even under high power regulation. So there is no any issue, because I showed you an example. We regulated this converter from 400 volt to 206 volt. All the capacitors are well protected, no issues, because we also use the capacitors here. Every stages we use the capacitors, so no issues. It all depends on the PWM methods, how you adapt along with your driver. So driver plays a critical role for ensuring the reliability of your capacitors. Of course, all the devices.
Thank you. But is there any sensor actually? It is fabricated in capacitor and other electronic device in the same components. So sometimes it is drainage.
Yeah, I understand your question. We can't keep your sensor inside the capacitor. No technology is available because it's a, yeah. So we need to sense all the parameters. Only possibility is the current. So one parameter most important is the current, because current is the charging parameter of the capacitor. It's a current control device. It's not a voltage control device.
Correct.
So we need to sense the current. That's why I said we are keeping all the monitoring the current. So if there is any irregularities in the current through the inductor, obviously it affects the capacitors. So we always keep the ripple content within the limits of less than 5%. I say 5%, but for this application, we kept less than 1%. So it's sufficient enough. And there is no any spikes. You can see with the performances, there is no any spikes. Obviously, a short spikes obviously affects the capacitors, blow off the capacitors. We are ensuring all this through proper design of gate drivers. So your gate drivers, that's why a separate research is going on, designing gate drivers. So when your gate drivers are well equipped to all these sort of short transitions, then your capacitor is well protected, because capacitor characteristics can be improved by two plates and its air gap medium or through other medium of isolations. But what you can do more than that, capacitors can blow off if there is any short spike. So ultimately the burden is on the driver. So driver should take the responsibility to keep all these signals within the limitations.
Yes, thank you so much.
Thank you very much.
That's why also additional information. That's why if you take any capacitors, you have tolerance plus or minus. So the tolerance why we are giving means, the manufacturer are giving means, we have to keep the spikes within that limits. So it all designed, so we have to keep the spikes within the tolerance limit. When you are crossing the tolerance limits, the capacitor will blow off.
Okay, Sarala PowerTech Consulting Engineers, you can now unmute and ask your question.
Hello.
Yes.
Hello. Yes, sir. Good afternoon, sir.
Yeah, good afternoon.
Hello.
Yeah, I'm here.
Yeah. Sir, actually, I have one question. Sir, DC-DC bidirectional converter. For that, is it a transformer-less design or you're with transformer design?
Our research are focused on transformerless design. In real time, of course, in electric vehicles for charging the batteries, obviously they use a transformerless converter. But in the future, obviously we are going for one area of focus, because everybody has their own vision. Every researcher has their own vision. So a transformer-based converter is also a sort of an replacement for charging the batteries, because you can fly off high current to the batteries. with the transformers. But I said there is a complexity because you need to properly design the, either it's a coupled inductor or it can be high frequency transformer. You need to design appropriately. Of course, you have to compulsorily use soft switching methodologies for the MOSFETs or IGBT. Otherwise, we can't be able to deliver the maximum power from the source to the load.
Sir, actually, we are also working on this in the same field, but our design is with transformer. But we tried for transformer-less design for the 48 volt to 400 volt, but it is quite difficult. We could not able to meet that, so we have gone finally for with transformer design. That is because we tried, but it is we could not able to maintain that.
But we are
Is
getting
it possible
here.
really?
We shown here an
Sorry?
example. We are shown here with the results.
Yeah, but
So this is all in R&D.
sir, is this actually, sir, I have doubt that is it practically means for industrial grade, is it possible to implement, or it will be like lab grade only? Just I have that.
No, as an academician, we are
right?
trying, as an academician, we are trying at laboratory scale. But when come into the companies, because for example, these components are designed with not surface mounted components. These are analog components which is available in a standard laboratory model. If you look at the drivers, we designed with surface mounted components. So when the surface mounted components coming to the picture, obviously there is a trade-off. These components are very effective with loss compensation when compared to the analog components. When comparing to the losses here, the losses here are very less. So when you are replacing all these components, surface mounted component, the converter structure will come down. As the converter structure is coming down, obviously there will be limited losses, because in the laboratory scale, the capacitors are tested for its reliability with these components, not with surface mounted component. Nobody is testing for the reliability. If you are testing for the reliability of a surface mounted component of a capacitor in real time, obviously much higher than these components.
Actually, sir, one more apprehension that even we are doing for surface mounted. Actually, all our design is maximum mixed manner, both through hole as well as surface mounted. Both is there. In our design case, we have seen that we have tried both microcontroller, both the DSP as well as the TMS for handling that bidirectional converter. But still, also we could not able to achieve that our efficiency. We could not able to go beyond 91%. That is one problem. Another problem got that we got our destruction. That harmonics is near about 7 to 8%. How we can minimize that? Even we are arranging that EMC filter and EMI filter, everything also we have intact in that. Is that what is the possibility cause? It is a possibility in the firmware, or it is possibility that selection device component. What is the possible cause?
Obviously, your component selection will be appropriate because you are from an industrial background. There is no any doubt, because obviously you might be use the best components available in the manufacturing side. Maybe one problem. Did you verify your transformer design? That's most important, because the coupling point plays a critical role in a resonant converter, because at what rate of frequency you are transferring the maximum power. One depends on your switching frequency. Your switching frequency should matches your resonant frequency. Otherwise, you can't be able to transfer the maximum power from the input to the load side. One problem. Another problem might be, are you using ZVS or ZCS? That's most important. 0 volt switching and 0 current switching. Because when you have a inductor, I'm not talking as a transformer, I'm talking as an inductor. You have a isolated inductor on your converter. Obviously, for the input side, your inductor is the load. Inductor is a highly non-linear system. So if you are triggering your input side converter, I'm not sure what type of converter you are using on the input side. If it is going to be a standard inverter with high frequency, I don't know what is the model. Suppose if you are triggering your input side converter with a normal PWM, then you can't be able to transfer the power maximum from the source to the load. You have to think on working on 0 volt switching is not enough. You have to go also with 0 current. When both 0 current switching and 0 volt switching simultaneously has been done in your converter on the input side of the converter, obviously you can be able to deliver the maximum power from the source to the load. So I'm not sure what type of converter configuration you are using. Then I can go inside also for you.
Yeah, okay. Actually, sir, if I can get your some personal interaction, means I can a better way I can explain you, sir. Even I can make
Okay.
one video call and I can show the our work also, if at all possible, sir. If
Happy
you
to
have
collaborate.
time,
With pleasure, we
can
can
give
collaborate.
some
Yeah,
time.
why not?
Yeah, if at all possible, sir, can I get your contact information like that?
Definitely, I will share you.
I get partner.
Yeah.
Okay, right, fine, sir. Sir, one more doubt, sir, I have. Sir, actually, as per whatever your design you have till now made, for that, what type of microcontroller you are using, sir? Basically, TMS controller or
We are using
USB?
FPGA because we are working on the laboratory scale. For example, even we
Yeah.
use Arduino. A simple microcontroller Arduino we used
Okay.
because we are controlling
Okay,
only two devices or one devices, and sufficient enough to go for kilohertz. Still, we didn't try these converters in megahertz because if you go for megahertz, then all the component size will come down. So it all depends on the funding, and so we are working out with the possibilities what are we are having, and for us the most important is the configuration. First, we are focusing on the configuration. First one is how we are overcoming the barriers. This is the two goals. Then application is like we are developing the converter with the availability of the component and of course on the price, the cost, because that plays a critical role for the academician. But we are an industry, so you obviously spend the money for the components. We can't spend like that. So selection, that's why I said in my presentation, selection play a critical role. Again, I tell you, maybe for your converter, the problem may be two impact, I believe, because one can be the design problem of your coupled inductor or a coupled transformer, which is working as a resonance circuit.
Yeah.
And if you're going to use what type of resonance circuit you are using, I don't know, because in the standard we have only two possibility. One is it can be an inductor or is a combination of LC. Is a combination of LC, we can have a tank circuit. Yeah. So in this case, I'm not sure what type of modulation you are using for the converter. If you are using a proper modulation, no problem. If you are using hot switching,
actually, sir, we are making space vector modulation, sir. Space vector modulation, sir, for our switching. Our PWM is space vector.
Okay, I understand. Now, I think I'm talking on DC-DC converter. You are talking on inverter, I believe. You are talking about the inverters.
Yes.
No, yeah. Inverter. Sir, actually, this is our system we have made it. That is one case is DC to AC conversion plus again one transformer we are keeping in between plus that AC again will convert to DC through just simply one diode bridge. Just like a bidirectional case, means two different bridge are there. Two MOSFET bridge. Both MOSFET bridge are one bridge will act as AC to DC conversion, like just rectifier. Another case, it will be work like DC to AC inverting action. Means the same bridge will act as a rectifier. Same bridge second time it will work as inverter. I think you must have getting my point.
And the intermediate, you have a transformer.
Transformer, yeah.
Oh, okay. It's a fully controlled converter. I understand now. Then you use a diode bridge to connect to your battery.
So diode, separate diode we are not using. That MOSFET is having one anti-parallel diode. That diode is acting as a rectifier bridge. I think you must be getting, sir. That MOSFET, which MOSFET we are using for inverting action, same MOSFET across one anti-parallel diode is there. The diode will act for rectifying action.
Okay, I understand now. It's clear. So please email me the details. So it's like a knowledge transfer between the academic and industry is always good, because obviously if you are using space vector modulation, you understand you can't get the maximum region. The maximum allowed region is only 86.6. If you well aware about the modulation factors of the space vector modulation, if you use space vector modulation, you can able to track the maximum voltage DC bus is 88.6. If you know well about space vector modulation, then how you can expect I want to go for 100%. There is a possibility in space vector modulation you can go up to a range of 102 is possible, but the most important drawback is you will get distorted current. Then your current will not have less harmonics, it will have more harmonics. You understand what I'm saying?
That is only problem. That is problem.
Then in this case, you can't say I want to go for 99.91%. It's not possible. Efficiency of an inverter is always less than a DC-DC converter. There is no doubt at all.
Yeah.
Okay, sir.
Efficiency for, I don't know very clearly about, I understand bit, because you said you are using a rectifier and you are using a space vector modulation is right, because you convert your AC to DC. But again, I tell you,
Yeah.
space vector modulation, you can go up to the sinusoidal margin. I mean, you can able to get a very good sine characteristics. Only maximum is 88.6%, 0.886.
Yeah.
Is not possible
Correct.
above. If you are going over modulation
Yeah.
region, you will have a distorted current, and there is no compensation techniques for a distorted current until now, my knowledge, because it's a factor. Either you want a very high voltage, I want to get near to 100, yes, I can go at 100, near to the 100%, but you will have a distorted current. There is no compensation.
Okay, sir. Thank you very much.
Okay, sir. Thank you. There is
Anybody has
only
any question?
yes, one more question was raised. Mr. Moinak Mukherjee, you can ask the question.
Hello, sir. Good afternoon.
Yeah.
Actually, I want to know that from power system in power electronics application, if I work with a hybrid energy system, what is the best way to deal with the stability issue?
Stability all depends on your information. First of all, you should know, as I said in my presentation, what type of combination, because I said very clearly what type of combination is plays a critical role, because it's going to be a combination of PV and fuel cell, or PV and battery, PV and
Yes,
wind. So it's a combination. So then before putting into the application, you should know the characteristics. Otherwise, we can't be able to regulate the both hybrid power in a expected demand requirement. So most important is the characteristics. You should know the characteristics when you can be able to get the maximum power with proper regulation from the PV. So you need to have a characteristics of a PV. Of course, when you are using parallelly even a battery, PV and battery, then you should know the battery characteristics. So that's why if you look at the data sheet of any manufacturers, obviously it comes with the product, because they give you the characteristics in experimental condition in the laboratory model. Of course, some companies gives in real time. Then you will have an idea this is going to happen in real time. Before putting into the application, as a researchers, we also test them before connecting into the real time. So we test separately each systems for its characteristics. Then we connect in a hybrid model for our requirement. So
actually, I'm working in PV wind model. So facing difficulty in PV dynamic modeling, that means small signal stability analysis. So that's why, can you refer any question or any book that will be best for me to know the fundamentals that I can show that I can proceed further, because there is a problem regarding islanded grid.
Yeah, I can show you something. Good book from best book from Aalborg University, from Professor Freddie Blabzer and Professor, if I'm right, his name is from Professor Freddie Blabzer. There is a book on grid connected converters. So if you send me an email, I will share you.
Okay, thank you, sir.
It focused mainly on wind technology.
Okay, sir, can you share your email ID, please? Okay.
Yes.
Hello, sir. Electrical department will give you the email ID. If you contact later.
Okay.
Yeah. Thank you very much.
Sir. Thank you very much.
Okay. Do you have
my email ID is here?
Yeah.
Okay, sir. Okay, sir.
I'll already shared.
Thank you, sir. Thank you very much.
Thank you. Is there any more questions?
Any more questions from audience end? Okay. Thank you very much.
Okay.
Mr. Paul, want to say something, sir? I'm asking Mr. A.K. Paul. You want to say something, sir?
Maybe one or two lines. Actually, the thing, the way it has been explained is very nice. The electric vehicles is coming to big cities, like in Calcutta and other cities, coming in a big way. So we must have to update ourselves with the present, with this technology, or this converter for which can be used in electric vehicles. And here we have seen that in the presentation that Professor has explained the losses in the converters, and for each component losses has been tested and identified. So we can find out the maximum efficiency. And here he also explained the maximum power tracking point, multi-objective converter. And another interesting thing is the vehicle to grid, which we can utilize for more power generation when the vehicle is idle. So all these concepts we can use. And we have also seen that how ultra capacitor can be used for increasing the stability, improving the efficiency, and hybrid model using two sources when there is a demand is more, all these aspects has been discussed. So it was a very interesting thing, and we have also learned something, and we can utilize this knowledge for improving our society. So thank you very much, Professor sir.
Thank you, sir. Thank you, Mr. A.K. Paul, for summing up the whole topic. And now, moving on to the next item, that last item, I would like to request Dr. Tanaya Dottodas, HOD Electrical Department, Techno India University, to propose the vote of thanks.
Thank you, Dr. Rajubhashak. On behalf of my department and other representatives of Techno India University, I extend my heartfelt gratitude to Dr. Padmanaban for sharing with us his work in the area of power electronics converters. I would also like to thank Professor Dr. Reena Paladhi, Director of Techno India University, for motivating us to organize this webinar. I am thankful to Dr. Raju Boshak, Mr. Ashok Kumar Pal, Mr. Ravi Ranjan, Mr. Shayan Chakrabarti, and other members of Electrical Engineering Department and Institutions Innovation Council for actively organizing this webinar. Finally, it has been a tribute to host such an wonderful audience. We are thankful to you and wish to see you in all future events. Good evening and have a good day.
Finally, I'd like to thank the management of a Techno Indo institution, Dr. Raju Baisek, the director, and Dr. Pal, everybody, of course, Dr. Tanya, giving an opportunity to have an interaction for more than 1 hour. Thank you, one and all. Have a nice day. Go ahead. Bye.
Right.
Okay,
Thank you.
thank you, sir. Thank you. Dr. Raju and Dr. Tanaya. So that.
Sir.
Everything, sir. Thank you, Dr. Raju and Dr. Tanaya.
Thank you, sir. Thank you very much.
Now I'll try
Thank you.
So now I'll try to see. My recording was going on, but 2 times the internet got disconnected.
Okay, I have recorded the entire event. I do not know it is recording in cloud. So let me see if I can retrieve it.
Okay, I'll also see. So I'm stopping.
Okay.
I'm stopping. Then okay, I'm leaving.
No, actually, that is
Okay,
the
sir.
asset for our electrical department, because the speech was excellent.
Speech was excellent.
Full of technical information.
See, shall we take that in the